Hello from Fairbanks, Alaska. I'm Jen Delamere, Director of the Geographic Information Network of Alaska, or GINA, on the University of Alaska Fairbanks campus. GINA is a direct broadcast partner of NOAA's Joint Polar Satellite System, or JPSS. In broad context, such partnerships ensure that satellite data is delivered as quickly as possible to operational forecasters and hazard managers in areas of the world where surface observations are sparse. And is Alaska such a place? In today's presentation, I'll be talking about how wildland fire management in Alaska benefits from the JPSS GINA direct broadcast capabilities, with particular focus on the Bureau of Land Management's Alaska Fire Service, or AFS. Established in 1982 and located in Fairbanks, AFS leads BLM's statewide fire and aviation programs and provides fire suppression services for over 244 million acres of Department of Interior and Native Corporation lands in Alaska, north of the Alaska Range. The JPSS program and GINA provide critical satellite information to AFS and its partners across the state. The low latency delivery of imagery and products, typically within 15 to 25 minutes of a JPSS satellite overpass, helps fire managers plan strategies to protect Alaska residents and businesses from wildfire disaster. The image in the center of this slide was created at GINA using data from the VIIRS instrument flying aboard the SWOMI NPP satellite, and it's a great launching point for this talk. Alaska has a surface area of 670,000 square miles, with a land area almost about a fifth of the size of the contiguous United States. 1/3 of its surface area is enclosed within the Arctic Circle, 5% of its area is covered by glaciers, and 80% of active volcanoes within the United States lie within its boundaries. On this map, wildland fire perimeters are plotted from 1940 to 2019. Fire happens in our roadless areas as well as on the road system. With 700,000 residents, 400,000 of whom are in the Anchorage area, our population density of 1.2 people per square mile is the lowest in the United States. The vast and varied nature of Alaska's landscape, population, and land ownership demographics lead to a range of wildfire management responses, from immediate suppression actions to periodic surveillance. As I pivot to the discussion of wildland fire management, I want to recognize that the content of this talk, while delivered by one, me, is the work of many. In particular, I want to recognize Jen Jenkins, Gary Schmunk, and Willie Branson at AFS, Allison York and Robert Zeal at the Alaska Fire Science Consortium, Curtis Seaman at CIRA, our partners at SIMS, and GINA staff Carl Dierking, Pete Hickman, Jay Cable, and Greg Worth. What do fire managers and fire behavior analysts need to know about active fires? Over the last 50 years, the tools that Alaska fire managers have to chisel out these answers have changed markedly. As Randy Jant at Alaska Fire Science Consortium recently noted, early wildfire detection in Alaska relied on keeping an eye on neighborhoods and on lightning storms. Much of the detection around the state was done by aerial patrols beginning in 1973. In 1978, BLM had 12 aircraft dedicated solely to fire detection, and another 6 smoke jumper aircraft, which often did loaded patrols after widespread thunderstorm activity. But by the turn of the century, yes, 20 years ago now, weather satellites were an important new tool in the tool chest. MODIS, flying aboard Terra and Aqua, was of great utility in 2004, the year with the largest acreage burn in Alaska, totaling an area about the size of Massachusetts. Smoke from scores of fires floated over eastern Alaska and western Canada. With a spatial resolution of 1 kilometer, MODIS fire heat points, or hotspots, shown as red dots on the image, were made available to the Alaska Fire Service by GINA. Note, AFS did not actually have the ability to access those images in near real time in 2004. They simply took the latitude and longitude of each pixel and the confidence value of the potential hotspots and turned them into spatial data on a map, sometimes even hand-drawn. Those points were then put into GPSs on airplanes and possible fire starts were investigated. By late summer 2015, the Alaska Fire Service was able to expand their toolset again, this time by bringing in GINA-computed heat points from VIIRS, the Visible Infrared Imaging Radiometer Suite, aboard SNPP. VIIRS has a higher resolution than MODIS, as high as 375 meters depending on the band, and maintains higher resolution out to the edge of the swath. Notably, 2015 was the second largest fire season by acreage since 1940, burning an area the size of Connecticut and Delaware. Imagery was becoming easier to access in near real time as the technology behind web portals and web applications advanced. This GIF from Curtis Seaman shows not only smoke generated within Alaska, but also advecting in over international boundaries. The air in interior Alaska goes from clear to so smoggy, the air quality rivaled that of industrial Beijing. The smoke is discerned from clouds because it is duller and brownish gray. And in 2019, another year where wildland fires were crossing urban boundaries and the number of fires to manage was daunting, AFS began using VIIRS almost exclusively, as it was now flying aboard two satellites, SNPP and NOAA-20. NOAA-20 leads SNPP by half an orbit, or about 50 minutes. With direct broadcast data received on GINA antennas, we see 16 to 18 VIIRS views of some point on the north coast of Alaska per day, 10 to 14 views for central interior Alaska, and 6 to 8 views for southeast Alaska. On this day in July, over 19,000 VIIRS heat detections were derived from direct broadcast imagery received and processed at GINA. VIIRS channel configurations, and at 375 meter to 750 meter spatial resolution, are useful for assessing and highlighting fire characteristics such as fire color and fire temperature, yielding information on fire extent and active burning. These images are made available in near real time to wildland fire managers. Also in 2019, the utility and availability of Landsat 8 and Sentinel-2 data had strengthened the hand of wildfire managers in Alaska. High spatial resolution images are incredible for mapping wildland fire perimeter and providing insight into fire behavior. An image is available every few days for Alaska. Note that these images are not received via direct broadcast at GINA. So sometimes quality comes in the form of quantity, such as VIIRS imagery, with multiple views per day coming via direct broadcast to GINA, catching breaks between clouds. And sometimes it comes to those who wait, such as for the Landsat and Sentinel imagery. And in the most critical of situations, it can come from unmanned aircraft systems. But rest assured, at the start of the 2020 decade, wildland fire managers in Alaska have considerably advanced remote sensing technologies to answer the wheres, hows, and whats associated with each wildland fire. So while I've shown you the timeline and examples of satellite imagery utilized by AFS, what I have not shown you is how GINA receives and processes that data so quickly. We are so far north, yes, close to the North Pole, that polar orbiting satellites overpass numerous times per day. So if you have receiving stations on the ground in Alaska to capture the data as satellites flow overhead via direct broadcast, and you can process it on site, you'll have a faster turnaround time than if you wait for a global data dump every few hours. GINA manages 2 receiving stations in interior Alaska, Big Dog and Sandy Dog, with access to a third in Utqiagvik, Alaska. We receive data from 10 polar orbiting satellites. Data from individual passes is consumed into GINA's near real-time processing stack. That is, a couple of big racks of fast computers. Our operations dashboard shows the flow of data from arrival to product creation. Each satellite we receive has a different workflow with different software packages. For VIIRS, after pass arrival, sensor data records are created using SIMS Community Satellite Software Package, CSPP. From there, fire color and fire temperature RGBs are created. For the VIIRS fire heat points for the Alaska Fire Service, we use NASA's Direct Readout Labs IPOP software, VFire 375. The algorithm takes as input VIIRS 375-meter SDR files, along with associated terrain-corrected geolocation files, and identifies active fires. A selection of geotiffs is delivered to the public via our Puffin Feeder web portal. Puffin Feeder is populated with images around the clock, and you can visit anytime at feeder.gina.alaska.edu. I don't have time to describe the incredible utility of each type of image available, but I encourage you to visit Curtis Seaman's VIIRS blog for great information about the different imagery. GINA's fire heat points or heat detections are made available now via Esri REST feature services. This means any web map application can simply add a new layer via a URL back to GINA servers. As an example, the Swan Lake fire, ignited by lightning on June 5, 2019, was managed but not fully suppressed on the Kenai Peninsula 28 air miles south of Anchorage, Alaska. Under incredibly dry and windy conditions, on August 17th, the fire spread across the Sterling Highway, a major thoroughfare that goes south from Anchorage. The fire was over 160,000 acres at that point. It was during this fire that GINA's Fire Heat Points feature service came online, so AFS consumed it into their Alaska Wildland Fire Information Map series. This service is broken down into temporal classes, all points from all satellite overpasses within the last 12 hours, 12 to 24 hours, 24 to 48 hours, and older. The service is automatically updated with each new satellite, SNPP, or NOAA 20 overpass. Moving one step beyond the VIIRS Fire Heat Points feature service, GINA is deploying an Esri REST image service so that GINA's near real-time fire imagery can also be easily consumed by web map applications. According to an article in Wildfire Today, quote, during the night of August 25th, some motorists on the highway found themselves driving past a crowning timber fire that was approaching the highway with what looked like 50 to 75-foot flames that were, in some cases, very close to the road. On the left is a VIIRS fire color image from August 26th. Fire managers now have tools to analyze remotely sensed data, a fire perimeter outline in red, roadways in black, and then you can toggle fire heat points from given time intervals of 12 to 24 to 48 hours or more to see when something like a roadway is crossed. What I've talked about so far is an operations approach to wildland fire management, but GINA's direct broadcast facilities can also be used in research to operations. Dr. Christine Weigel at the University of Alaska Fairbanks has developed VIFTAL, the VIIRS I-band fire detection algorithm for high latitudes, to detect fires in the Alaska boreal forest with higher sensitivity than the global VIIRS algorithm. Dr. Weigel implemented an automated processing chain to produce daily VIFTAL detections based on data directly downlinked by GINA. The image on the left shows the VIIRS standard high-intensity detections for the Swan Lake fire on July 17, 2019, while the image on the right shows many more low-intensity detections from using VIFTAL. In August 2019, that fire actually took off again from some of these areas that had low-intensity detections. This illustrates the benefit of low-intensity or residual combustion detections in addition to high-intensity detections. Fire management agencies like AFS are interested in this data for monitoring purposes. And finally, an example that puts all this together and was featured on the National Park Service website in June 2020. Quote, on Wednesday, June 17th, Denali National Park and Preserve received notification that a satellite had measured a heat detection from within the boundaries of the park and preserve. Upon notification, the National Park Service fire personnel coordinated with BLM's Alaska Fire Service to investigate. A detection aircraft was dispatched to the area. Upon arrival, the aircraft observed a smoldering fire covering approximately 400 acres, creeping with isolated torching. The fire was burning in an area composed largely of tundra and black spruce. The fire, number 248, was named the Bear Paw Mountain Fire. So there you have it. JPSS VIIRS imagery plays a critical role in Alaska wildland fire management. JPSS data is received and processed at GINA facilities. Data is then shared with state and federal agencies, and now wildland fire management teams have easy access to this wealth of data. Truly productive partnerships stemming from the JPSS program supporting direct broadcast facilities in remote locations like Alaska. I've covered much ground in this talk, but you don't have to remember it all. GINA's website will point you to links for data products, training videos and briefs, and specific project resources for the JPSS program. Thanks for viewing this presentation.